All right, guys, welcome to this short podcast on general solution of trig equations, as well as a look at some of the more non-standard trig equations you may encounter. Next year, you'll be looking at trig equations where you'll have to use double angle identity formulas. However, we'll save that for next year. Something to look forward to. Okay, so general solutions are more prevalent in Spesh than they are in methods. So even though you've seen the routine in methods, it doesn't hurt to go over it again in the context of the Spesh course. All right, guys, consider these three trig equations. Now, no domain, no restricted domain is specified. And of course, each of those functions are defined over the reals, although tan has exclusions at the each of its asymptotes. So does it make them impossible to solve? No, it doesn't. Even though they each have infinitely many solutions, we have the ability to express them using some pretty clever notation. All right, and that's all about the general solution. All right, guys, you can see before you three trig equations. There is no restricted domain. In fact, they're defined over the implied domain, suggesting we need to find a general solution. In fact, it's even stated, but if it wasn't, that's what you'd be, that's the implied understanding. Okay, so this approach is one of several that we can look at. I'm going to only focus on the one, and it's the simplest of the lot. That is, find two solutions in one cycle for sine or cosine, one solution for tan, and then just add k lots of the period. So it's really that simple. Okay. By saying k is the understanding that it's a member of the integers. Choose n if that's your preferred parameter. Okay, so having a look at cos, of course, basic angle, where is cos positive, first and fourth quadrants. There we are. Two undeniable solutions to that equation. In fact, if I replace x with pi on 3 or 5 pi on 3, left-hand side equals right-hand side. That is, after all, what a solution is intended to be. Okay, now what's the period of this function? Okay, you don't see a coefficient in front of the x, it is equal to 2 pi. So each of those solutions is separated by a multiple of 2 pi from another pair of solutions. So I can summarize all of those solutions as follows. So taking one solution, pi on 3, plus k times the period, 2k pi, and the other the other solution, 5 pi on 3, plus k times the period, plus 2k pi. You can make it one whole fraction from there, factor out the pi if you wish. You can play with that form, but that's a legitimate expression of the general solution. Infinitely many solutions are being suggested by that form, k being a member of the integer. You can take any old integer, whack it into that rule, and you'll find two solutions from it. Okay, having a look at tan, dividing by root 3, basic angle is pi on 6. Now for tan, we only need to find one solution per cycle, dividing through by 3, there it is, pi on 18. What's the period of this particular creature, this equation? It's equal to pi divided by 3. Remember, the period for tan is pi, so there it is. And so pi on 18 plus k lots of pi on 3 gives us our general solution. It's that easy. Okay, the third equation is a sine equation. Dividing through by 2, basic angle, of course, guys. That's right, pi on 4 quadrants where sine is positive, first and second. There we go. Two legitimate solutions in one cycle. The period for this guy is as it was for the cosine equation, 2 pi. So pi on 4 plus k times 2 pi for one solution, 3 pi on 4 plus k times the period 2 pi gives us another infinite set of solutions. So replacing k with -1 or 17 or 243 gives us any solution imaginable from that equation can be expressed in the form you see below you, with k replaced by some integer value or another. Okay, guys, now one complication of the general solution is the fact that there are infinitely many ways in which it could be a general solution could be accurately described. Now let's look at the the previous example of cos x equals 1/2, we legitimately came up with a general solution pi and 3 or 5 pi and 3 plus 2k pi. Now, it may well be in the back of the book, they've got general solutions described as 2k pi plus or minus pi and 3. Now, we weren't wrong, but in fact, what we've got here are two different expressions for the same infinite string of solutions. So to highlight that, let me just grab a pen. So what they probably did to come up with this kind of a form is that when they solved cos x is equal to 1/2, using a basic angle of pi on 3 and quadrants first and fourth, so basic angle is pi on 3, quadrants is first and fourth, they, rather than go 2 pi minus pi and 3 for one of the two general solutions, so here's my first quadrant solution, they've gone 0 minus pi and 3 or minus pi and 3. Okay, so of course that's two solutions in one cycle, a cycle from maybe minus pi to positive pi. You get those two solutions, and why not grab those? They're two legitimate solutions. Each of them will also be separated by k lots of the period. So it leaves the general solution expressible as 2k pi, so k lots of the period, plus pi and 3 or minus pi and 3, which could be summarized as plus or minus pi and 3. Okay, it's slightly neater. Oops, is equal to x. So clearly a legitimate solution. And if you're ever in doubt, what you can do is actually just substitute a string of k values. So let's have a look at k from -1, 0, 1, etc. So in this form down here, form number 1, we can say when k is equal to -1, it's describing x is equal to pi and 3 minus 2 pi, so that becomes minus 5 pi and 3, and 5 pi and 3 minus 2 pi, which becomes minus pi and 3. When k is equal to 0, we've got x is equal to, obviously, pi on 3, 5 pi on 3. When, k is equal to 1, not x, I think I said. When k is equal to 1, we've got 7 pi on 3. So pi on 3 plus 2 pi is 7 pi on 3. 5 pi on 3 plus 2 pi is 11 pi on 3, and so on. Now, let's have a look. Let's grab a different color. Let's have a look at this one over here. Okay, and let's go through the same k values. When k is equal to -1, we've got minus 2 pi minus pi and 3, which is minus 7 pi and 3. And we've got minus 2 pi, that's minus 5 pi and 3. When k is equal to 0, we've got pi on 3 and minus pi on 3. When k is equal to +1, we've got 2 pi plus, so we've got 7 pi and 3 and 5 pi and 3. Now, if you have a look, let me just finally grab a different color. 7 pi on 3, 5 pi on 3, 7 pi on 3, 5 pi on 3. Pi on 3 minus pi on 3, pi on 3 minus pi on 3, minus 5 pi on 3, minus 5 pi on 3. And of course, you've got 1 down the bottom end, but you're going to pick those up with other values of k with the next successor in at k equals 2, where obviously I'm going to pick up my 11 pi on 3. K equals -2, you're going to pick up your whatever it was, the other one that wasn't k equals -2 for this one, you're going to pick up -7 pi on 3. You're going to generate the same infinite string of solutions, and that's the important thing to realize. So if ever you've got a general solution that you've arrived at and you look at something, quite a different expression, don't be alarmed. Possibly you're correct, and you just have to ensure that your expression is indicating the same infinite string of solutions as the one in the back of the book or the one in the multiple choice question, and maybe by just subbing in some k values, is the way to go. Alternatively, if you can somehow see how it was generated using the method you know, that might be that would be a quicker approach to matching your expression for the general solution with the given expression for the general solution. Okay, so we've already gone through these solutions. Now it's possible, and it's quite a common feature to want to create a single fraction. So here we go. So there's one form of the solution, and factoring out, making it one whole fraction, factoring out the pi, that's a common form you'll see in the back of the book. Similarly, for the example we've already seen, 3x is equal to plus pi and 6. That's another way you could go about it, but I'm not going to worry about that for now. Making it one whole fraction, factoring out the pi, and you get those alternative expressions that look quite different. So, and similarly for the sine expression, you can see making it one whole fraction, factoring out the pi, and you get a form that may match the back of the book or whatever worksheet you happen to be working on. All right, so guys, here's something you should take note of in this sort of a question. If it was on your test, your next Spesh test, solve the equation. Notice no domain stated, so it's the implied domain, and therefore it's the general solution, expressing infinitely many solutions, and hence find all solutions in the interval minus pi to pi. Now, if you went on and just worked out all solutions in the interval minus pi to pi, not going via a general solution, you'd actually get 0 marks for this question. So please note, that's what's being asked for in the question. So how do you go about it? As always, move all terms to the other side of the equation. You're solving for the argument of the function 2x plus pi on 3. Basic angle pi on 6, quadrants of obviously third and fourth, sign being negative. So we set up our third quadrant and our fourth quadrant solutions with respect to the argument. We then subtract by 2 pi and 6 both and divide through by 2, and we arrive at two particular solutions. Through the method discussed, we identify the period of this function. 2 pi divided by 2 is equal to pi. Oh, that's a very small line. The period is equal to pi. So I take both of those solutions and say plus k pi, got a bit of punch, or n pi if you're an n person, where k is an element of the integers. And we're done. That's a general solution. Now to progress from there to the part 2, the hence is the key word there. We just have to sub in various values of k until we cover the domain from minus pi to pi. Okay, what do I mean by that? Let's sub in k equals 0, because clearly 5 pi and 12 and 3 pi and 4 lie between minus pi and pi. Let's try now k equals minus 1. So if I subtract pi from each of those, I get minus 7 pi and 12, certainly less than minus pi, and minus pi and 4. All good. Let's try k equals 1. So if I add pi to each of those, I get 17 pi and 12 and 7 pi and 4. However, they're both beyond the upper bound of the domain, so they don't count. Okay, guys, let's now consider a couple of non-standard trig equations. So this is now beyond sine or cos of an argument equals a numerical value, and you need to use your exact values. Clearly there's something extra we need to do to an equation of this form. And any equation, the rule of thumb is look to factorize first and apply the null factor law. So in this particular example, we've got a common term, and that's sine x, and that leads us to think immediately of factoring out sine x. And we're left with a quadratic factor, sine x. So sine x is equal to 0, or cos squared x minus 1 is equal to 0. But difference of two squares means we can further factorize that as cos x plus 1 and cos x minus 1. This, via the null factor law, leads us to 3 individual equations, okay, that we need to come up with general solutions for each, because a domain was not stated. So sine x is equal to 0. Obviously, we've got multiples of pi would be equal to one solution. So what is it? Just in order to solve equations of this particular form, what we need to do is think about the unit circle. So when sine x or cos x is equal to 1, we should be thinking about this creature here. Okay, and obviously sine x will be equal to 0 at those 2 points on the unit circle at multiples of pi. Don't forget, this point over here is even lots of pi, takes us there, and odd lots of pi takes us to that point on the unit circle. So at either even or odd lots of pi, we're at the x-axis along the unit circle, which means any multiple of pi, k pi, could be seen as a legitimate solution to sine x is equal to 0. What about sine x is equal to -1? Well, in fact, sine x equals -1, sine x equals 1 is absorbed in that solution anyway. So when sine x is equal to -1, we're over here on the unit circle. So in fact, that could be seen as all values of x that are odd. So 2k plus 1 pi, where k is an element of the integers, and cos x is equal to 1 takes us to this point on the unit circle. In other words, x is equal to 2k pi. So all even numbers, as we've seen before, can be expressed generally as 2k. All odd numbers can be expressed generally as 2k plus 1, where k is an element of the integers. Now you can see each of those, all odd multiples of pi, all even multiples of pi, has already been absorbed into the solution for sine. Sine x is equal to 0, so this is an unusual case where they don't actually contribute to our particular expression of the general solution, and we are done. Okay guys, now let's have a look at another non-standard equation, and that would be something of this form. Immediately look to take out a common factor. There is none, but you can see, hopefully some of you should be able to see, it's in fact a hidden quadratic. There's a squared term, a linear combination of that term, and a constant. So a great way to bring out the quadratic function, quadratic equation, is to make a substitution. Let's a equals to sine x, and we've got 2a squared plus a minus 1. And you can see that's a neatly factorizable quadratic, as 2a minus 1 is one factor and a plus 1 is another factor. Now you could solve for a at that point, or do as I've done and substitute sine x back into the equation. Once it's in its factorized form, in linear factors, it's neatly solvable there. So going through that process, we get two equations emerge. Sine x is equal to 1/2 and sine x is equal to -1. So of course anything of that form, unit circle, okay, remember sine x or cos x equals plus or minus 1 or 0. It's all about the unit circle. It's that point there on the unit circle is what we want to generalize. Let's go back to the first one. That's a more standard equation to solve. Basic angle what? Pi on 6. Quadrants, where is sine positive? First and second. So let's click on the next line. So we've got pi on 6 plus k lots of the period. So obviously here's my quadrant 1 solution. Quadrant 1 solution. 5 pi on 6 plus 2k pi is my quadrant 2 solution. So plus k times the period. The period of sine x, of course, is equal to 2 pi. So a quadrant 1 solution plus k times the period, which happens to be 2 pi. Quadrant 2 solution plus k times the period. And there's some other versions. Now, what about this other equation? Generally, that's, of course, 3 pi on 2, or in fact, it's equivalent to minus pi on 2 in terms of the angle. And obviously, the period is equal to 2k pi. So we're going to grab minus pi on 2. I could have easily grabbed 3 pi on 2 plus k times the period is my next infinite string of solutions. So that's how you do it. It's all about factorizing and null factor law, breaking it down into linear factors where you can. Hopefully that's all good, guys. Okay, this is the last one to highlight before you complete the worksheet that will appear in Teams for you guys. Okay, so basically when you've got some multiple of sine equals to some multiple of cos, and the key is that they have the same argument. Okay, so this approach only works when it's the same argument. then what are you going to do? You're going to divide both sides by cos and convert the equation to a tan equation. Yep. So hopefully that's clear enough. Dividing by cos of that same argument, it becomes a tan, the argument is equal to b, divide through by a, and you've reduced it to a tan equation. So really they're just hidden tan equations. The key is the argument must be the same in both sides. Okay, so have a go at this equation. Pause if you wish and come back to the vodcast when you're ready. Okay, I'm going to proceed with the solution. So I notice it's some multiple of sine is equal to some multiple of cos, and it is the same argument. So what I'm going to do is divide both sides by cos of that argument, 2x plus pi on 2, divided by cos 2x plus pi on 2. And lo and behold, the coses will cancel on the right hand side, and I've reduced the left hand side to tan. So it becomes root 3 tan 2x plus pi on 2. Can only do that with the same argument as I said. Dividing through by root 3, so tan 2x plus pi on 2 is equal to 3 divided by root 3, which is equal to root 3. Multiplying top and bottom by root 3, you should be able to see that. Okay, I might change the color because I don't like red particularly. Okay, basic angle is equal to pi on 3. And quadrant, I only need to worry about one quadrant, whereas tan positive, it's certainly in the first quadrant. And now I can begin my general solution. Don't forget you're solving for the argument to begin with. 2x plus pi on 2 is equal to pi on 3. Okay, solving for x, so subtracting by pi on 2. So pi on 3 is equal to 2 pi on 6 minus 3 pi on 6 makes it minus pi on 6. Okay, dividing it through by 2 gives me one solution, minus pi on 12. Okay, of course there isn't a domain specified, so it's the implied domain. So all solutions can be expressed as follows, as x is equal to minus pi on 12 plus k times the period. Now the period will be equal to pi divided by the coefficient of x, which is 2, plus pi on 2 times k, where k is a member of the integers, any member of the integers. Let's now just clean it up because what the hell we can. So it's minus pi plus 6 pi k, all on 12, and just factoring out the pi, so it becomes 6k minus 1 pi, all on 12, where k is a member of the integers. Now, if you had a different expression, just check that it's equivalent to mine, indicating the same infinite string of solutions. Okay, guys, that should take us out for now. If you could have a go at the attached worksheet, and I'll see you on Friday. Bye-bye.